Welcome. At the beginning of Chapter 11 or Topic 11, the discussion is about uncertainty in data. And as you talk about uncertainty in data, there's really two things you have to focus on, and that's the idea of what are called random errors and systematic errors. And the second thing to focus on is whether it's affecting your precision or your accuracy, which are two slightly different things. So uncertainty typically is the name used for random errors. And they're called random errors because they could just as easily influence your data upward or downward. But because you have uncertainty, it limits the conclusions you can draw. It gives you a range in which your final calculation actually lies. So uncertainty can result, like I said, in results being high or low, but we account for it by propagating the uncertainty through our calculations. And we can determine the uncertainty that any instrument gives us by looking at how precise that instrument is. Does it measure to 1 milliliter, to 0.1 milliliter, etc.? And then the other error that we tend to see in our data is called systematic error, but these are caused by poor experimental design or procedure, and these will cause a deviation in one direction only. For example, if you read the top of the meniscus rather than the bottom of the meniscus when you're taking readings in a graduated cylinder barrette, reading the top is always going to inflate your value. Another common example is heat loss from a calorimeter. Heat loss from a calorimeter is always going to deflate your values. So systematic errors only cause the uncertainty to move one direction or your deviation in one direction, but random errors can go either direction. Systematic errors, more trials are not going to help, whereas random errors, more trials will tend to average it out or minimize the effect of it. So when we're using instruments, the precision of the instrument is what allows us to determine the uncertainty. So what does the word precision mean? Precision means how consistent your results are, whereas accuracy means are you getting the correct result. So accuracy, you can refer to either your average or a single result and look at how close is it to the expected or desired result, whereas precision, you have to look at a series of results and see if they're closely clustered. Are you getting the same answer consistently? And ideally, we want to see both in our results. So the precision of the instrument is what determines the uncertainty, and it will determine part of what will determine the uncertainty is whether you're using an analog or a digital. So first of all, you're expected to be able to choose the correct instrument for what you're doing. For example, if you're going to measure 25 milliliters of water, a beaker would be a poor choice because it's got very few markings on it and it's not intended to measure out precisely. But a graduated cylinder or a pipette or a barrette would all yield much more precise measurements and give you a much smaller uncertainty in your measurement. So for an analog or a non-digital instrument like a graduated cylinder or barrette, the uncertainty is 1/2 the smallest division indicated on the instrument. So on the left, you'll notice that my graduated cylinder is marked to the nearest 1 milliliter, so I could estimate to the 10th place, and my uncertainty would be 1/2 of that 1 milliliter, or plus or minus 0.5. The graduated cylinder on the right measures to 2 milliliters, so now my uncertainty is 1/2 of the 2 milliliters, or plus or minus 1 milliliter. For a digital instrument, like most of our thermometers and our pH probes, the uncertainty is equal to the smallest division indicated on the instrument, unless the uncertainty is specifically stated on the instrument. So for this particular thermometer, I can see that it's measuring 37.0 degrees Celsius, so I would express the uncertainty as plus or minus 0.1. Other sources of uncertainty are your timing. When you're timing, like your reaction time, you'll have to estimate how quick you think your reaction time is or try and make a measure of it. When you're using color changes, especially indicators, your judgment of when the color has changed and how consistent that color is all add into your uncertainty. So uncertainties like this are hard to quantify, but you should definitely mention them when you're talking about your results. Quantified uncertainty that you can actually get from the instrumentation is given as a plus or minus, again, because random uncertainty can occur in either direction. So qualitative data is all non-numerical data that you obtain from your observations. So qualitative data should always be included in your lab report, especially if any of your measurements relied on an observation, like a color change, or when dissolving completed, or when gas was no longer being released. And you want to discuss how you kept that as precise or consistent as possible. You can also bring qualitative data in when you're discussing your analyzed results, your calculated and processed data. It certainly would be appropriate to bring in your observations at that time. And the last thing to mention in this video is the idea of significant figures. Significant figures in a measurement include the smallest increment for digital instruments, or the estimated digit for analog instruments. Generally, if zeros are significant in a measurement, we use scientific notation. For example, 1.00 times 10 to the second would let me know that all three digits are significant, whereas if I write 100, it would appear that there's only one significant figure. And the rules for carrying forward significant figures are pretty straightforward. When you add and subtract, you keep the number of decimals used in your least precise measurement, whereas when you multiply and divide, you keep the number of digits used in the least precise measurement.